second talk today. Speaker is Professor Takuzo Okada from Kyushu University, and title of his talk is Birationally Solid Fano Threefold Hypersurfaces.
Thank you for the introduction. And first of all, I would like to thank the organizers for the invitation to Taipei and to this conference. And today, I will talk about the birational geometry of Fano varieties and especially on birational rigidity and solidity, which I will explain. So first of all, let's consider rationally connected, for example, three-folds, and modulo birational equivalence. We can choose representative as modifiable spaces, and so which divided into three types. One is Fano with Picard rank 1, and the other types there is vibrations over rational surfaces and with terminal, in the category of terminal singularities. Okay, okay. And conic bundle over rational surfaces, And so for example, the P3 lives in here, the overlapping area. And today I talk about this area. Okay, so let me give a definition. So now let X be a rational surface. Yes, it can be singular, because I am thinking about the modifiable spaces in the terminal and the Q factorial categories, so So let X be a Fano variety. So in my talk, this means terminal and Q factorial.
Sorry, if X is a Fano variety, then RC threefold, so S should be what singularity?
In general, it can have dual singularities.
Dual?
Yeah. Yes, in this definition, this can be any dimension, but I'll consider Picard rank 1. So I say X is birationally rigid. So, okay, how to say, okay. Any modifiable space in the terminal and the Q factorial categories, which is birational to X, is actually isomorphic to X. So this is a uniqueness of the as a modifiable space in the birational equivalence class. So clearly, such Fano variety, if it's threefold, lives here. It cannot be birational to any other types of modifiable space. And this is a very strong notion. And I want to consider weaker notion. I say that X is birationally solid if any modifiable space birational to X is a trivial modifiable space, meaning that it is Fano variety with Picard rank 1. So in this definition, X can be birational to other modifiable space, but the modifiable space is necessarily trivial. I mean, it's Fano with Picard rank 1. So, yes, so rigid one lives in this small area. So the solid one is, it's generalization. So this property implies the irrationality of the polarity, since it cannot be birational to P3. Okay. So the aim of my talk is to, I am very interested in this area, and I want to understand which Fano threefold lives here. Yeah. So first of all, let's consider known examples on hypersurfaces in arbitrary dimension. So let's consider let X be I put D here. Smooth hypersurface of degree D, and which is Fano, so we consider this part. And so if the degree is the top degree, then it is well known that this one is birationally rigid, and after the many contributions, the Ferner.
The original version, birationally rigid was under the condition that the birational automorphisms are just automorphisms. But
In this definition, I do not impose any conditions on birational automorphism. But but actually we have more stronger notion. It is called super rigid, and it says that it is rigid, and the birational automorphism coincides with biregular one. This is even more stronger. And in this sense, this is super rigid for this one. Yeah, and
birationally solid for a Fano form that would say that it is not ruled.
do not?
If you have a Fano form,
Yes.
it is birationally solid.
Yes.
That implies that it is not ruled. That it does not admit a rational map to the surface whose fibers are rational terms.
Actually, right, yeah. Yes. So, this is a Fano index 1 case, and so once we consider higher Fano index cases, the rigidity immediately fails. So, So hypersurface lives in this projective space, and let's consider general linear subspace of codimension 2, and consider projection from this linear space to P1, and if we have a resolution of indeterminacy, if it just blow up, okay, just blow up, this one is modifiable space by this condition, and non-trivial, of course, over P1. So not birationally rigid, and clearly not even solid, because it has a modifiable space over positive dimensional base. Okay. So we are done with the hypersurface, smooth hypersurface cases, and so from now on, I concentrate on the three folds, and in this case, we do not have an example of solid one, which is not birationally rigid. So it is either rigid or non-rigid. So we don't need this notion here, but from now I concentrate on Fano threefold, and which is still hypersurface, but embedded in a weighted projective space. So let me explain a setting. So let's consider Fano threefold, I mean terminal and Q factorial. X, and we only consider hypersurface of degree d embedded in some weighted projective force space as a hypersurface. Of the degree of the defining equation is d, I put here, and the weight of the coordinate ai as described here. And we assume that okay, let's write P. This is very basic assumption. The space is well formed, meaning that A4, this one is 1. This is not so, this is small assumption. And the next one is more important. So this corresponds to the smoothness of the usual hypersurface in the projective space. But yeah, I assume k-size smoothness, and by definition, the affine cone is smooth outside origin. Sorry, in my talk, everything is over C. Is smooth outside the origin.
What's wrong with not well formed?
Not well formed. Some pathology happens, but we can always consider transform this one into a well-formed one. So this is kind of basic setting. Yeah. Yes. So from the beginning, I assume that X is Fano. So with this assumption, this X has only terminal cyclic quotient singularities. And next, set the Fano index in class group. I mean.
So if we choose the along the edge of the equal, we have a canonical quotient singularity.
Canonical?
Canonical quotient singularity. If we choose the bottom edge of the equal.
Yeah, but in the, I assume that X has only terminal. So I define Ix to be this one. So we have the class group is isomorphic to Z. And this number is divisibility of the Kx in class group, not Picard group. Sorry, minus K, sorry. So minus K is OX, IX, yeah. So I briefly explain the classification of this K-size smooth hypersurfaces, which are Fano threefolds. So first of all, we have the index 1 hypersurfaces, and there are 95 families, and this means that 95 tuples of weights and degree. Okay, and in the higher index cases, there are 35 families. And next, so okay. And from now on, I will explain the known results. So first of all, by the result of this theorem is due to Iskovsky-Manin for quadratic three-fourths, and then some other contribution. Chertoff solved the following result. So for the 95 families of index 1 case, the X is birationally rigid. So, no. Every case size smooth one, yeah. Yeah, this kind of result, it is usual that someone prove with some generality assumption, and then they remove this assumption. Okay, next, so I explain what's going on for the higher index cases. So they continue the study of the cases of higher index together with Hamid Abban. So they obtain the following result. So they consider this case, and okay, I always assume that weight is satisfies this order. Sorry. So the first, the least common multiple is equality. Okay, strictly smaller than index. So in this case, they show that X is not birationally solid, and this can be seen easily. So let me quickly explain. So suppose we have X with this assumption. This assumption, okay, and then let's consider projection to this weighted projective space. Then this okay, and take some resolution of singularities and the indeterminacy of this projection. And this condition ensures that the fibers are uniruled. So then we are running a minimum model program over this space. We get modifiable space. So this is necessary non-trivial. Yeah, this is not the explicit example, but we somehow know the existence of some non-trivial modifiable space. Okay, so now we have two types for the higher index cases, and one is this case, and we have 30 families with this assumption. And the rest is so the rest is of course 5 families. So this is the second assumption. So they show that it has some other birational model, which is Fano threefold of Picard rank 1, which is birational to X. And of course, it's not isomorphic to X. Yeah, as I said, we have 5, but this 5 can be divided into again 2 types and. Sorry, this 130 families are numbered according to the lexicographic order. So this 5 corresponds to these 5 families, and yeah, we have 4 families with index is 2, and the last one is the index 3. And in this theorem, if X is index 3 hypersurface, then we have one more. So it's very complicated, but I put check. And yeah, it's not isomorphic to the previous models. So, okay, in this case, X is not birationally rigid. So, this is their result. And so the natural question is this one, whether it is solid or not. So here is the main theorem of my talk. And yes. More precisely, if the assumption, the second assumption, is satisfied, then we don't have any other model. So these are all birational models as a modifiable spaces.
Are they all single or some of them are smooth? Are these all single?
This one, singular, yes.
Are there smooth examples which are solid but not?
Smooth one. So far, there is no such example. So far, okay. If we have this kind of phenomenon, so far we always have a divisorial contraction to some singular points, so we don't have smooth examples so far. Yeah. Maybe we may expect in in higher dimensional cases. So from now on, I explain the proof of this result, or I want to explain some birational geometry of these models. So, okay. So I want to explain some generalities on the proof of birational rigidity or possibly solidity. So okay, in this section, so I explain it in a general framework. Let X be a Fano variety with terminal and Q factorial singularities with Picard rank 1. So, so the fundamental theorem is the Sarkis program, which says that any birational map between modifiable spaces a composite of some elementary one. And I don't recall the details of this program, but I want to mention the elementary links from this Fano threefold, the Picard rank 1. So elementary links from X. Okay, X, I mean X. Fano variety of Picard rank 1. There are two types, which I explain. So one of them can be decomposed in the following way. So first consider some divisorial contraction from everything is terminal category, terminal and Q factorial. The divisorial contraction in this category, and there is some tau is a birational map, which is isomorphism in codimension 1, and followed by some divisorial contraction to another model. So this one is an elementary link of one type. In this case, this model is Fano is Picard rank 1. And the second one, it is similar in the beginning. Let's consider some divisorial contraction from Y and consider birational map, isomorphism in codimension 1. And the target is a modifiable space. So in this case, target is necessary, non-trivial. Anyway, we have two types. And one thing I want to remark, here is that elementary link is always initiated by a divisorial contraction. So basically, we want to understand the birational models of X. So because of the soft program, it is enough to consider or classify elementary links from X or from some other models. So in this case, it is very important to consider divisorial contractions which initiate some link. So next, but how to check the given contraction is initiates a link or not? It's not easy, but here we have a definition. So suppose let phi be a divisorial contraction. Here X is a Fano variety of Picard rank 1. And let E be the exceptional divisor and to center. And I say that I say that this contraction is maximal. If there exists a movable linear system, so because X is Picard rank 1, we always have some rational number n. So let's denote n. This is a definition of n. If there exists a movable linear system, on X, such that this pair is not canonical along E. So I mean, the pullback of M and the coefficients, multiplicity of this base locus along E is greater than this number. Yeah, this is a non-canonicity along E. So, okay, if we have a maximal contraction, then in this case, we call its center maximal center. So the proposition, if so let phi be a divisorial contraction, and if if it initiates elementary link, then it is maximum. So, yeah, this is the explanation is simple. So, we have this one, and if we have some link, then link to some y prime or x prime, depending on the types. So this M can be constructed by putting back very ample, sufficiently ample, complete linear system to y here and push down it here. So it has some, it creates linear system with high multiplicity. So, okay, this is a generality of the proof. So we can detect elementary link by the contraction, and we need to consider which it is maximal or not. So, any questions? Okay. So, okay, with this generalities, I explain outline of proof of theorem for the most complicated case, the three model cases. So this one is sorry. This one is degree 20y hypersurface in here. And another two models can be described as follows. The first one is also hypersurface. And hypersurface of this one is index. Sorry, this is 3, and this one is index 1. And as I explained the Chertsov-Pack result, if this is k-size smooth, then it is rigid. So it cannot be birational to X. So here, this variety is not k-size smooth. Yes, and the third one is a complete intersection of codimension 2 defined by degree 6, 7 equations inside some weighted projective space. And this is also index 1 and non-KSI smooth. So meaning that these two have Gorenstein terminal singularities. So I will explain later. So the strategy is simple according to this framework. So for each divisorial contraction from X, whether first shows that it is sorry. It is not a maximal contraction. In this case, this initiates no links, so we can ignore this contraction. Or otherwise, construct a link. Initiated by this one. And once we are given a divisorial contraction, the link, elementary link initiated by this one is unique. So if it exists, so okay, this is an important remark. So this is a strategy, but clearly we have infinitely many contractions, so we need to consider all of them. And also, so do the same for the other models. So, okay, I explained. The part one. Part one is called the exclusion of maximal contractions, maximal centers of contractions. So we have many methods to exclude a given phi as a maximal center. So I cannot explain all of them, and I only explain the most basic one, called 4n squared inequality. So let V be a germ of a smooth threefold. And let M be a mobile movable linear system on V, and N is any positive rational number. And if this pair is not canonical at the point P, then the multiplicity of the self-intersection of this general two members, this is a one cycle on V, and it has high multiplicity at P. So basically we want to show that the given divisorial contraction is not maximal. So if we assume contrary, we have some divisorial contraction to smooth point, then there is by definition, there is a movable linear system vanishing along P with high multiplicity. And so since this pair is not canonical, we have this high multiplicity. So from here, we somehow derive a contradiction by computing some intersection numbers. So, okay, this is a very rough explanation. So this is the most basic method to exclude smooth points as a center of maximal contraction. So we have some variants for the singular cases or the case of curves, and so I explained the classification of maximal centers or contractions of X and the other models. So first of all, we have smooth points. On these three models, and this can be excluded mainly by this result, and some other cases we need to tackle some by other method, but anyway we can exclude all of them. So next, and I can also exclude curves for these three models. The problem is the singular points. The singular points on X, we have two. And X has only cyclic quotient singularities. And it has 2 points. And in dimension 3, terminal quotient singularities have a unique divisorial contraction centered at given terminal quotient singularities for any three-dimensional terminal quotient singularities. So the situation is very simple. We need to check this unique one is maximal contraction or not. So the answer is okay. This is maximal, but from this center we have a link. Sorry. Link to these models. So I explain. Link. So we have a birational map elementary link from x to x hat and also to x check. These ones corresponds to the initiated by this divisorial contraction with these centers. So we are down with x. Sorry. This is hat. And sorry, I don't have enough time. So let's consider hat. Sorry, hat. We have three singularities. And I exclude this center as a maximal center by, I can exclude them. And from this center we have a link. I write iota, which is involutive birational involution. And finally, okay, this C7, this is the most difficult part of this result. And from this, I can prove that there exist exactly three divisorial contractions to this compound E-type singularity. We have three. And okay, I don't have time to explain the details of these contractions. But anyway, this one is divisorial contractions of discrepancy 2, and the other two are discrepancy 1. Anyway, we have this divisorial contraction initiates the inverse of, inverse of this one. Okay, so this one is a divisorial contraction to these CE points. And this one is a divisorial contraction to this model. And the last one is not a maximal contraction. Sorry, finally, okay, I finish in 1 minute. So finally, we have two singular points for this model. And one is a cyclic, and the other one is a compound D-type singularity divided by Z2. And this one, let's do the inverse of this link. And this one is also problematic, but there is a unique divisorial contraction. I prove that there is a divisorial contraction centered at this one, and this one leads to the inverse of this one. So all the contractions are, all the links are classified, and so we don't have any more link to some other model. So this is the proof of main theory. Thank you very much. Thank you.
Are there any questions or comments?
This result by Aban Chelsea Park saying that there exists this X hat, assuming that the index is smaller than or equal to LCM, etc. So is there an easy formula to produce the tape, the weight for X hat from those of X?
Formula to produce some.
So because the X hat is also a weighted
hypersurface.
So my question is whether there is an easy formula giving the weights for X hat.
There is some machinery, but So we start from X, which is embedded in some weighted projective space, and so given some point, we consider some weighted blow-up here, and we always consider some embedded weighted blow-up, and this one is a rank 2 toric variety, and we can, it is very easy to run two-ray game. I mean Sarkisov program to this toric variety, P hat, and see what happens for the image of Y. It is very easily observed, and this one has a toric contraction morphism to some toric variety, and it is usually weighted projective space. Sometimes not, but usually it is weighted projective space, and the image is simply the link.
So on the weight, the formula is explicit.
So we need to. There is some machinery, but it depends on some cases. So it's some machinery, but it's complicated.
I had another complicated question. Among these varieties, many because that they are certainly not rational. So do you know anything about the stable irrational?
First of all, I skipped the explanation, but maybe about 5 years ago, I checked the stable rationality by the specialization method, and I consider reduction mode P method, Totaro's one, and I checked that many of them, for example, this one's not stably rational, but as you know, for very general members, this one and this one are not stably rational. But in this result, I don't need generality.
Please.
In this example that you drew at the end, number 110, does having this complete description of the lengths provide you any insight into the birational group of X? Basically,
I can, because any birational map of birational automorphism can be decomposed with this one. I can, theoretically I can understand, but it is too complicated to me, so I did not challenge. Yeah.
Are there any other questions or comments? If not, thank you very much again.
Thank you.